हेलो एवरीवन, नमस्कार बच्चों। तो हम अब अगले स्टेप में आ गए। अब एप्लीकेशन जो हम लोगों ने अभी पढ़ा है डाइपोल में, इलेक्ट्रिक डाइपोल में एप्लीकेशन उसका होने वाला है किसका, कूलम्ब्स लॉ का, इलेक्ट्रिक फील्ड इंटेंसिटी और सुपरपोजिशन ऑफ फील्ड्स एंड फोर्सेस। तो ये सब होना है। तो अभी हम जो देख रहे थे इलेक्ट्रिक डाइपोल के बारे में, इलेक्ट्रिक डाइपोल मोमेंट क्या होता है कि नहीं। इलेक्ट्रिक डाइपोल मोमेंट उस दिन अभी पिछले वीडियो में बात हो रही थी कि ये इट इज वेक्टर क्वांटिटी, इट इज इक्वल टू प्रोडक्ट ऑफ चार्ज ऑफ वन मैग्नीट्यूड ऑफ चार्ज एंड सेपरेशन बिटवीन द चार्जेस इन द डाइपोल। दिस इज n suppose, or this is unit vector p. Okay, its direction is from negative to positive charge in the dipole here. So this its direction is p here. Okay, so next to it we have to see electric dipole in an external electric field. So this is known to you. When a charge is placed in an external electric field, then it experiences force. Very simple. Suppose at any point strength of external field is E and a charge of magnitude Q is placed here, then certainly this charge will experience electrostatic force in the direction of electric field. Okay, and this will be like this. So this is QE, because QE. So dipole is what? It is system of charges. So if a dipole is placed in an external electric field, then both charges will experience force due to field, and that force will be according to F equals QE. So let us draw quickly. Okay, so nothing we have to discuss special. So let us see here torque acting on the dipole when it is an external electric field. So let us draw. Suppose this is electric field, uniform electric field. Okay, uniform electric field can be represented by equispaced parallel electric field lines. So here this is electric field, and a dipole, an electric dipole is placed in this field, keeping this charge here, and suppose a positive charge is here, and this is dipole. So let us draw the dipole properly here. Okay, so its dipole moment is what? It is directed from negative charge to positive charge. Okay, or it is along the axis. So this positive charge, this magnitude of charge is plus q, magnitude of charge is minus q here, and these charges will experience force parallel to the field. Okay, so force on electrostatic force on the positive charge, it is in the direction of electric field, external electric field, and suppose field is here, it is marked here. So this charge will experience force in this direction, and magnitude of this force will be QE, and this force is QE vector. And here also this is negative charge here. So at this point and on this charge, due to field, force will be here. This is minus QE, opposite to the field. This negative is for opposite to the field, force opposite to the field. So this is force on negative charge, and this is force on positive charge. But magnitudes, clearly magnitudes on both of charges will be same. So F positive will be equal to F negative. Okay, so see, if field is uniform, these forces are forming a couple. Couple means these are two equal or opposite forces which are acting on a dipole, and if there is couple on the system or on a body, certainly the body will tend to rotate in the direction of torque provided by couple. So, see here what is direction. These two forces, they are tending to turn this dipole clockwise. So, see, this is clockwise. So, clockwise turning is possible here. So, certainly what will be torque? So, remember all materials studied in 11th class in the rotation. So, torque acting on a body, or you can say if a couple works on a body, magnitude of torque we write arm of couple, okay, arm of couple and multiplied by net force, or sorry, multiplied by magnitude of one force, magnitude of one force. So, see, arm is what? Arm is perpendicular separation between the forces acting on the body. Since these forces are equal forces in magnitude and opposite in direction, and so their lines are here. So, perpendicular separation between lines of these forces is how much? Let us see, this is what, and you know conventionally this length is written 2a, and here, okay, and direction of dipole or dipole moment, this dipole moment is representative of dipole, it is characteristic property of dipole. So, direction between or angle between this field and dipole moment will be taken into account. So, this direction, this is angle theta between the directions of dipole moment and electric field, and same theta is here, okay. So, arm of couple, this is what? Arm of couple. So, one force, magnitude of one force multiplied by arm of couple gives magnitude of torque acting on the dipole in the field. So, this is very simple to calculate. This is application of your gained knowledge. So, nothing difficult is here. So, let us write again. So, when an electric dipole is placed, okay, in an external electric field, external electric field which is uniform, means it has same intensity at each and every point, then what will happen? Then its two charges will experience a torque due to electrostatic forces acting on, okay, sorry, uniform, then its two charges will experience force only, then total dipole will experience torque, will experience electrostatic forces acting on them due to field, which give rise couple, okay. So, this couple and torque due to couple will be what? Then torque due to couple means what? Couple means this is a pair of equal and opposite forces acting on a body. These form couple. So, torque due to couple is how much? This is magnitude or magnitude of torque here, magnitude of torque, I am writing magnitude of torque. So this is how much? Arm of couple multiplied by magnitude of one force. Okay, both forces are equal in magnitude. So magnitude of one force means any force. So this is what arm is. How much? See here, this is 2a, this is angle between P and what? Electric field. So this is 2a and this is 2a sin theta. Arm is 2a sin theta. Okay. If dipole moment is it's so oriented that if dipole, how much? If dipole is so oriented that its dipole moment forms angle theta with what? With the direction of electric field. Okay. Then arm of couple equals 2a sin theta, and magnitude of one force, okay, magnitude of one force is what? This is Q into E. E is what? From left to right. Then easily you can write, this is how much torque is? This torque is tau equals arm of couple means 2a sin theta multiplied by QE. So take EQ here. So 2aq and E sin theta. And what is 2a into q? You know well, this is magnitude of electric dipole moment of the dipole. So 2a into q, it is magnitude of electric dipole moment of the dipole. Okay, and it is vector quantity. Again, dipole moment is vector quantity, electric field is vector quantity, and torque, you know well, this is also a vector quantity. So torque is how much? This Pe sin theta, its magnitude of torque is Pe sin theta. And see from figure, what is direction of tau? This is clockwise torque. So it is negative or positive? Clockwise torque is always negative. So it is inward. If a torque tends to rotate this system clockwise, or it works clockwise on the system, then certainly it is in the inward direction. According to right hand rule, you can see here this torque is inward. Clearly this torque is inward because it tends to rotate this system or this dipole clockwise, so it is inward. Then certainly it is a vector quantity, E is vector quantity, P is vector quantity. So this torque, it must be obtained due to vector product of P and E. So vector product of P and E should be there. So it should be P cross E or E cross P. So see from situation here, this torque is acting clockwise, then it is inward according to right hand rule. If one quantity is here, other quantity is here, torque is here, so A cross B, this will be torque in upward. A directed here, B directed here, then torque will be here. So P is here, E is here, torque is inward, then certainly we have to write P cross E, so that this product must follow right hand rule. Okay. According to right hand rule, this should be how much? P cross E. So let us write in vector form. This is magnitude of torque. Okay, many times it is used in numericals. So magnitude of torque is here, and in vector form, and in vector form, it is how much? Torque is P cross E. Okay, this torque is P cross E. And what is unit? We didn't talk about this. So unit is what? If Newton is there, meter is there, this is meter, sorry, this is in meter length, length means arm, this is force in Newton, so Newton into meter, it gives joule, so it is joule or Newton meter, so Newton meter or joule, it is unit. Okay, now see the cases or situations. This is field for uniform, this is for uniform field. What would happen if field would be non-uniform? Means at this place, suppose field value is different here from this point, then certainly these forces would be different. So here, if field is uniform, these forces cancel each other, there is no net force. They are giving torque in this position, but there is no net force on the dipole. So definitely here there is translational equilibrium. There is no rotational equilibrium in this orientation, but there is translational equilibrium because net force acting on the dipole is 0. These two forces are equal in magnitude and opposite in direction. But again I am saying, what would happen if field is non-uniform? Definitely these forces will be non-equal in magnitude, and then certainly there will be some acceleration in the direction of larger force. If field is stronger in this region, this force F on negative charge or F negative will be larger in magnitude in comparison to this force, because field is smaller here. Again see, these charges are of same magnitude. So charges are equal in magnitude. If field differs, then certainly forces will be in different magnitude. So remember this thing, in that case there will be a translational inequilibrium, or you can say there will be acceleration in the direction of larger force. So here, if here field is stronger, acceleration will be in this direction opposite to field. If field here in this region is stronger, then acceleration will be in the direction of field. So this situation. Otherwise, if field is uniform, there will be no field. There is no net force. So see the cases. Again, some cases are there in different orientations. What would be torque on this system? So case one, what? Stable equilibrium. Stable equilibrium. What is this? Stable equilibrium means if object, it acquires such orientation that it tends to remain in that orientation. If it is slightly disturbed from this position or this orientation, it comes to again the same orientation. Okay, so it has tendency to maintain the specific orientation. This is stable equilibrium. So in this case, this is what? When P becomes parallel to the electric field. Means these two forces, they are pulling apart this dipole, they tend to align this dipole in parallel to the electric field, then certainly P here, it tends to get aligned in the direction of E, and this is tendency of dipole, and that is why dipole moment is taken along the direction negative to positive, because it has a natural tendency to acquire that orientation. So, if when dipole comes to its stable equilibrium, we say its moment has aligned in the direction of field. Okay. So, that is why dipole moment of electric dipole is said to be in the direction from negative to positive, because in a stable equilibrium negative will be here and positive will be here, negative will be left and positive will be in right. Okay. So, this is about this logic of dipole moment to keep from negative to positive. Okay. So, stable equilibrium is that, means this is the lowest energy position, we will discuss later about this thing, stable equilibrium. This is what, when angle theta is 0, okay, this is most stable orientation, okay, most stable orientation, and that time torque is how much? Torque equals theta is 0, then torque, magnitude of torque is 0. And so, in each and every case, when torque is 0, net force is 0, this dipole will be in equilibrium. So, if field is uniform, translational equilibrium will be there always in any orientation, but there will be rotational inequilibrium, or there will be torque, non-zero torque except this position, except 0 and 180. So, if theta is 180, this is unstable equilibrium, this is also equilibrium. In this position, torque becomes 0, net force is also 0, net force again it is 0, it remains 0. So, unstable equilibrium, it is what? When theta is 180 degree, again sin theta is 0. So, torque, magnitude of torque is 0. So, there is no net torque, this body or this dipole will be in equilibrium. But this is unstable equilibrium, because in stable equilibrium orientation, this dipole is pulled apart from left side, from right side, it is pulled like this. So, whenever it is disturbed from its orientation of stable equilibrium, it again acquires the position, it again returns to that orientation. Okay. But what happens if it is in unstable equilibrium? Here torque is 0. In unstable equilibrium, what happens? Again this positive, now this is positive charge, sorry, in stable equilibrium this is positive charge, this is negative charge, positive charge is towards right, negative charge is towards left, if field is from left to right. Okay. But in unstable equilibrium, what happens? This dipole is turned like this 180 degree, positive charge comes to left and negative charge comes to right, negative charge experiences force opposite to the field, positive charge experiences force in the direction of field. So, these charges of dipole, they are pushed like this. Okay. So, a compressive force acts here. Okay. So, these pairs of forces, they try to press this length, then certainly what is happening, this is equilibrium, though it is equilibrium, but it is unstable. Even if it is disturbed slightly, okay, if it is disturbed slightly, what happens? This dipole will turn like this, okay, this dipole will turn like this. So this is unstable equilibrium, still equilibrium, but in case of any disturbance it will shift to its stable equilibrium. Then this equilibrium is unstable equilibrium. So net force overall we can conclude here maximum torque. Now take the position of maximum torque. So third one is what? Third is how much? Maximum torque when theta is 90 degree, means dipole axis or P is perpendicular to E, means P is perpendicular to E. In these cases P was parallel to E, here also. So in this case tau maximum equals P into E in magnitude. In this orientation the dipole will experience maximum torque. So remember this thing, in case of uniform electric field, in case of uniform external electric field, if dipole is placed in that field, what happens? Net force is 0 always. In any orientation net force is 0, because two charges will experience always opposite forces. This is clear. And since field is uniform, okay, and torque will depend upon orientation. In stable equilibrium theta will be 0, positive charge will be towards right, negative charge will be towards left, and net torque will be 0. In unstable equilibrium positive charge will be left, negative charge will be towards right, if field, given that field is from left to right, and torque will be 0. Maximum torque will be in perpendicular direction, whether positive is up and negative down, or positive is down, negative is up. Dipole moment is always directed from negative charge to positive charge. So remember this thing. Okay. Now go to this field, what? Non-uniform field. Go to non-uniform field. Okay. What is there? If field is non-uniform, then certainly there will be no equilibrium, translational equilibrium. These forces may be different, magnitude of these forces acting on positive and negative charges may be different. So there may be acceleration. Any force may be stronger. If field here in this region is stronger, then this force is stronger. Force on positive charge is stronger, then dipole will be accelerated in the direction of electric field. If field near the negative charge is stronger, then certainly this force is stronger, force acting on negative charge is stronger, and dipole will accelerate opposite to the electric field. So this is all about this torque acting on the dipole, and dipole or torque, the physical significance of this torque and dipole moment, certainly we have discussed already. On molecular and atomic level, certainly this is very important. Torque acting on the dipole is important. When a polar material is placed in an external electric field, its molecule tend to acquire the stable equilibrium, they tend to turn in the direction of field. So they give rise electric dipole moment of the sample. Okay. This is a matter of discussion. So we will take another video for discussion on material and dipole moment, polarization and so on. But here I am closing this video, and let us move, and thank you very much to being with us.